Hey guys, welcome back to chapter 17. In this video, I'm going to introduce you guys to the second order and zero order integrated rate law equations. So without further ado, second order integrated rate law. So again, we're going to start our derivation with the two rate equations. So rate equals the disappearance of our reactant over a given amount of time. And then our rate law was that rate constant K, concentration of our reactant, and with this being second order, we have that squared value there. We set these two equal to one another, and then we integrate with respect to time. When we integrate with respect to time, we get the following equation. So again, your job is going to be able to recognize which equation to use and use that equation. No integration or derivation there. So what we see here is the integrated rate law for second order is going to be 1 over concentration of A at time t equals the rate constant times time plus 1 over the concentration of A at time 0. So again, we have rearranged it in this format because we've got an equation for a straight line. So what we see with that equation, let me remind you what that looks like. So y equals mx plus b. So what that looks like is on our y-axis, we are going to plot 1 over concentration of A. That's what we see right here. The slope in this case is going to be a positive slope, and again, that's going to be equal to the K value. So that's what we see is that slope is going up. That's a positive slope. And whatever the value is for that slope, that's going to be K. Our x-axis is still going to be time, so we see that down here. And then the y-intercept, where it intersects, is going to be 1 over concentration of A at time 0. Okay. So now that we have two different integrated rate laws, we can kind of set up a kind of make-believe example. So let's say I had this reactant A, and I was trying to figure out if it was first order or second order. So in the experiment, every, 100 seconds, I decided to take a measurement of the concentration of A. So 0, time equals 0, here's concentration of A. 100 seconds, here's concentration. 200, here's concentration. 300, so on and so forth. Then I'm like, you know what, I don't know if that's first order or second order. What we can do now is we can make two different graphs. So maybe the first graph, we plot time versus natural log of our reactant. And maybe for the second graph, we plot time versus 1 over the concentration of our reactant. Okay. And what we'll see here very quickly is this is a second order reaction. When I plotted it against natural log, I don't get a straight line. I get this kind of like slow curved line. It doesn't fit a straight line like it should. So I don't think this is a first order reaction. Then I plot time versus 1 over concentration of A. And I see these points match up to a straight line, much better than they did for natural log. So with these points matching that equation for a straight line, that indicates to me this is in fact a second order reaction. Now to solve second order reaction problems, you're going to see things very similar to what we saw for first order. So we would say something like, initially the concentration is this. After 300 seconds goes by, what's the concentration of A? And so then you would just use this equation to solve for that concentration of A. We'll see an example of this later on in the videos, but just kind of a preview introduction right now. The last one we have is a zero order. So same kind of format here. We have that average rate, concentration of A divided by change in temperature, change in time, wow. Rate law, rate constant K, concentration of A. There's a zero because it's a zero order. We write these equations equal to one another, so anything raised to the 0 power is 1, so they kind of took that out. So we've got K equals this average rate. We integrate both sides with respect to time, and here is our equation for a zero order reaction. Definitely the easiest, most straightforward reaction that we've seen. But the concentration of A at some time t is going to be equal to negative K times time plus concentration of A at time 0. We can still talk about the equation of a line just like we have before. So just as a reminder, y equals mx plus b. So our y-axis in this case is just the concentration of A. We don't have to do anything crazy. Our slope is again going to be a negative slope. That's what this negative sign tells us. And the value of the slope is going to be K. So we see that negative slope again. T is going to be our variable on our x-axis. We see that down here. And then the y-intercept is going to be the concentration of A at time equals 0. There's our y-intercept. Okay. And again, for zero order, we will look at problems where it says, initially concentration of A is this. After so many seconds go by, what's the concentration of A later? We can look at graphs for this. Again, let's say we did experiments. We wanted to decide if it was zero order. In this case, they were like, oh, I'm going to do 2 different molecules and find out which one is zero order. So we've got time on the bottom. We've got concentration of a reactant on the left. And we see in this case that the decomposition of tungsten would be zero order because that fits. That fits a straight line here. The decomposition of sulfur dioxide is not zero order because we get this kind of curved line. It doesn't fit that straight line. So if I had to pick which one of these was a zero order reaction, it would be the decomposition of tungsten. Okay. How will I know that on a test? You're going to want to focus in on the y-axis variable. So if it's concentration, it's going to be zero order. If it's natural log of concentration, it's going to be first order. If it's 1 over concentration, it's going to be second order. So keep an eye on that y-axis to determine what order the reaction is. Here's just kind of a summary slide that kind of pulls everything together that we've talked about up until this point. So we've talked about 0, first and second order. We've talked about rate law. We've talked about units of K. We've talked about integrated rate law, and then we've talked about their straight line plot. The only thing we haven't talked about yet is the half-life expression. We're not going to talk about 0 and second order, but in the coming videos, we will talk about the half-life of a first order reaction, so that is yet to come. But just a cool little summary slide as you're studying, something to maybe have handy as a reference. In the next video, we'll work some examples of integrated rate law with something other than first order. I hope you guys found this helpful.